Hello and welcome to today's lesson on the correlation of bivariate or two-variable data. Okay, our objective for today, by the end of this lesson, I'll be able to calculate the correlation value for the two-variable graphs and use that in descriptions of two-variable scatter plots. Okay, now when we're looking at any calculation, one thing that we want to think about is why do we need that calculation? What does it help us with? Now, if you think back to our last lesson, talking about direction and strength of a linear association, we had these sets of graphs. And moving from left to right, we went from weak to moderate to strong to perfect linear association. Okay, but that was just a description. Okay, what we want in mathematics is the fact that the correlation R gives us a numerical value so we can make comparisons between these. So we're looking down at this lower one. This one might have an R value of about a 0.2, okay, all the way up to the upper one of a 1.0. Okay, so we're really looking at that scale of values for R overall. And then R can also be negative. So this one could be down around a negative 0.1, okay, all the way up to negative 1.0. So when we're looking at that, we'll talk more about the scale of R when we look at the calculation and work through some of our values. So now when we look at the calculation of the correlation coefficient, how we go through the process, okay, it's a quantitative value, so it's a numerical value of the strength and direction of the linear relationship. And that's probably one of the most important terms here. When we're talking about this correlation coefficient, this is for a linear data set overall. Okay, when we're looking at our calculation, we want to think about some of our values here. We've got our sample size that we need to take into effect. Okay, this is each individual x value. Okay, we have each individual y value. And then we have our mean values for x and y. Okay, and we'll go back over how we find those. And then the sample standard deviation for x and y. That we also need to make this calculation. So this is a fairly intensive calculation. You don't have to do it too often, okay, but we do want to understand how the calculation is made over time. Okay, so let's take a look at an example. Okay, these were the data values that we saw from our last unit, comparing students' homework average to their final average in a random sample. And what we'll look at is we'll see, I already have the values up right now so that we can use those, but we want to review how we can get those values quickly. So once we have our information entered into the calculator, we've got our list 1, list 2 values of the two. We want to go back to statistics, function, calculation, and up until now there hasn't been much use to use the two variable stats over one variable stats, but now we definitely have the case where that becomes more beneficial, gets us all of our answers in one spot. Okay, so we can see here we've got our x bar, we have our s of x. Okay, so we're taking those values out. If we scroll down, we can see our y values as well. So our y bar, our s of y for the calculation. So now, if we're wanting to go through and do the calculation for R, okay, so R equals 1 over, our sample size is 10, okay, so we have 10 minus 1. Okay, that's a multiplier that's on the outside of this very large summation. Okay, so when we're looking at this summation, we're inside, we're taking each individual x value, 69 minus the mean value. Okay, so you can see we're kind of looking at a deviation calculation here, dividing by our standard deviation. Okay, this kind of normalizes that process. Okay, it looks a lot like a z-value calculation. Okay, and it should. You know, it is that type of calculation. And then we go into our y value, 75 minus y value average divided by y value standard deviation of 8.8. Okay, so that's just the first piece. And then we have to keep working through each of the individual pieces. I'll do a couple here. You know, remember when you're showing evidence in a homework problem, you want to make sure that you're showing the individual reading your test, that you can do any calculation that's asked of you. Okay, now we'll let the calculator do this work for us. Okay, and then once you've gotten down a few, okay, we can dot, dot, dot all the way to the end. Okay, and if we work through all of this, okay, we find out that this has a correlation of 0.72, and we want to understand what that means, so we'll talk about this with respect to a scale in just a little bit. And you know, in a couple slides here, I'll show you how we can get this R value on the calculation. But like I said, a very labor-intensive calculation if you have to do it by hand. Make sure that you know the formula is given to you on the formula sheet. Okay, so you have the calculation there, and then it's just a matter of plugging in the values and being able to use it. So now, when we look at the properties of R, okay, R values always lie on the scale from -1 to +1, because remember, this is also a directional value. It's direction and strength overall. So when we're looking at our possibilities here, for statistical purposes, what we do is we really kind of break things into chunks. Okay, if our R values are from -1 to -0.8, 0.8 to +1, okay, we call those strong associations when we're looking at that range there. Okay, and then we break it into the next interval from 0.8 to 0.5 in either one. This would be our moderate association. Okay, so you can see that the association between the homework and the final test averages, you know, is at the top end of the moderate. So you could say moderate to strong. And then we have our final grouping, you know, from 0.5 down, okay, would be a weak statistical association. Okay, in business, in real world situations, okay, the strong and the moderate might grow a little bit in size. Weak becomes a little bit smaller. Okay, but for statistical, you know, pure statistical purposes, you know, these are kind of our basic scales when we're looking at the R value overall. Now, what affects R? And truly, there's really only one type of thing that affects R. And I'll show you some situations that we just want to understand about what happens and what are some of the things that we can do with it. But the only thing that changes in R value is a change in an individual value, okay, or a couple values. If you make a few value changes, because this R value is not resistant to outliers. Okay, if you remember that term from earlier in the year when we talk about resistance. So it's not resistant to small changes. So now, if we want to find R, okay, we do it in our stat calculations, and R is connected to our linear regression, okay, which is what we're going to look at next. So we can do a little precursor here. And when we do our linear regression, okay, we can see that the calculator gives us that R value down below. So 0.717, 718. Now, let's do something a little bit different here. Let's change our two variables. Okay, so we're going to go stat, calculate, linear regression. Okay, but now I'm going to change this to list 2, list 1. So let's say that you flip the two variables and you mix up the explanatory response. Is that going to affect your overall situation? And if you notice, when we do our linear regression, it doesn't change that correlation value at all. It changes our slope and y-intercept of the linear regression line, but it does not change our R value as well. Okay, just one more quick show here. I'm going to go into stat edit. I'm going to make a new list where every one of my L2 values, okay, so I'm going to do enter so I can type into an equation. I'm going to do 2 times my list 2 values, and then add 7 to each of those. So 2 times list 2 times 7. Okay, now I've got this new list of values, but if I go in and do my linear regression, okay, comparing list 1 with this new list 3, notice we get the same R value overall. So any manipulation we make to an entire set of values or the entire list of values, both X and Y, has no effect on the individual R value or the correlation between those two, okay, because of how the formula normalizes all of those values overall. Okay, now, one reminder that I want to give you is this is only for linear data. Okay, we're talking about the linear relationship overall. Because if I look at this graph, most of you can probably name what this is. Okay, this is a very common relationship between two values, a quadratic graph. This quadratic graph has an R value of 0, but there is a definite relationship. Okay, but remember what the R represents. It represents a value connected to the linear relationship between those two values. Okay, so that's something that we're going to talk about as we get later into the unit as well. Now, one extra calculation. If you remember when we looked at the calculator, it gives us two values. It gives us R squared and R. So we want to understand what R squared represents. Mathematically, it is just squaring the R value. Okay, when we do that, we always get values between 0 and 1. Everything is positive. Okay, so we lose the direction of the linear relationship when we find an R squared value. But it's really, and I think this is one of the best terms I've seen, the explained variance. Okay, it tells us what proportion, okay, so this is actually a proportion or a percentage calculation of the variation in the Y values. Okay, so now we're talking about our vertical variation that is explained by our least squares regression model. Okay, so the higher the value, the better the model explains the response. Okay, so if we look at our situation, okay, and just looking at our R squared value, this tells us that 51.5% in the variation of final scores is explained by our least squares regression line. Okay, and like I said, we will talk about least squares regression line in our next unit. But when we're looking at this R squared value, okay, this is kind of what we call the percentage of fit, or the percentage of the Y variable that can be explained by this line. You know, not a great value over here overall, okay, and that's why we look at the R squared as a part of our work. Okay, one thing that we want to remember, correlation does not mean causation. We can find things that are very closely correlated, but there is no cause and effect relationship. Okay, we always want to look at the variables, and we always want to think about confounding variables. You know, so even in our homework versus final situation, you know, there are outside confounding variables that probably have a larger effect on that overall relationship besides the mathematical numbers overall. Okay, so now for your in-class packet, if you want to see some extra work or get some extra practice at these, it is page 2 of the in-class packet. Talks about the correlation calculation and some of that descriptive nature. Thank you very much and have a good day.